Module 2, Fractions and Decimals. This is section 2.2, Factors in Simplest Form. It may be necessary, when you're performing operations, to factor a number. Since 7 times 9 is 63, both 7 or 9 are factors of 63. 7 times 9 is called the factorization of 63. Factors are numbers that you multiply together to get a product. Those factors may be prime numbers, numbers that the only factor it has is 1 in itself. Composite numbers have multiple factors. An example of a composite number would be 16, because 16 could be broken down into 4 times 4. And both 4s are composite, because I can say 2 times 2 times 2 times 2 for the 4s. 31 is prime, though. There are no two numbers that you can multiply together to get a 31. 31 doesn't have any other factors besides itself and 1. 49, however, is composite, because 49 is the product of 7 times 7. When you factor a number down to a string of prime numbers, that is called prime factorization, where every whole number that is a part of the multiplying process is prime. The prime factorization of 30 could be written into the product of 6 times 5. 5 is prime, but 6 is also composite. So I can say 6 is 3 times 2. 3, 2, and 5 are all prime. 3 times 2 would give me the 6, and 6 times 5 is 30. So 2 times 3 times 5 is not just a factorization of 30, but a prime factorization of 30, as 2, 3, and 5 are prime. To find the prime factorization of 6, you would find two numbers that you can multiply by to get a 36. There's multiple choices, but let's say I say 12 times 3. 3 is already prime, but 12 is not. 12 is the product of 4 times 3. 3 is still prime, but as we saw on the other side, 4 is composite. That's a 2 times of 2. I take all the numbers at the end of the tree and multiply them together. 2 times 2 times 3 times 3 is the prime factorization of 36. We can write this using exponents and saying 2 to the second power times 3 to the second power. That is a prime factorization of 36. We already looked at the prime factorization of 30. See if you can find the prime factorization for B, C, and D. Pause the video and check your answers when you're done. Let's look at the answers for B, C, and D. 75 could be written into 25 times 3. 25 is 5 times 5. The prime factorization of 75 is 5 squared times 3. For 170, I can say 17 times 10. 17 is prime, but 10 is composite. A 10 is the product of 5 times 2. 17 times 5 times 2 is the prime factorization of 170. For 360, I can say 360 times 10. You can say a couple other things too, but that's just the first pair that I thought of. 36 is 6 times 6, where each 6 is a 3 times a 2. 5 times 2 will give me a 10, and now all the numbers at the bottom of my tree are prime, and I have 3 2s, 2 3s, and a 5, even though this 5 times 2 doesn't want to stay on the page. How do you know where to start? You can use some divisibility tests to help you find out where you can start to find factors. If a number ends in a even number, it's divisible by 2. If you add up all the digits of a number and it's a multiple of 3, then it's divisible by 3. And if it ends in a 5 or a 0, it's divisible by 5. I just start with 2's and divide by 2 until I can't anymore, and then I go with 3's, and if it ends with 5 or a 0, then I start with the 5's. Let's look at the prime factorization of 63. I know that 63 is divisible by 3 because 6 plus 3 is 9, and that's a multiple of 3. So 3 goes into 63. Well, 3 is going to go into 6 twice. When I multiply, I get another 6, so when I subtract, it's a 0. Bring down to 3, and 3 goes into 3 once. So 63, one pair of factors, is 3 times 21. Now 21, if you add the 2 and the 1, is a 3, so that's also divisible by 3. 3 times 7 is 21. All the numbers at the bottom of my tree are now prime. I have 2 3's and a 7. So that's one way that you can use divisibility rules to help you find pairs of factors. This will be very helpful when you have to reduce fractions. If you want to write a fraction in simplest form, then you want the numerator and denominator to not have any common factors. So you may need to use the divisibility rules, or maybe even prime factorization, to help you find these common factors so that we can reduce this to simplest form. To write a fraction in simplest form, you will write the prime factorization of the numerator and denominator, and then divide out by all the common factors. An example of prime factorization is in like letter A, where I have 10 over 42. Well, 10 is equal to 5 times 2, and 42 is equal to 21 times 2. Well, 2 over 2 is a 1. And so I'm looking at 5 over 21. 9 could be 3 times 3, and 27 is 9 times 3, which is 3 times 3 times 3, since 9 is 3 times 3. And so one pair of 3's will divide to a 1, another pair will divide to 1. When there's nothing left in the numerator or denominator, then there's an invisible 1 there. So 9 over 27 reduces to 1/3. For letter C, for 8 over 36, well, I know 8 can be a 4 times a 2. And I know 36 is 4 times 9. And so I can say these 4's divide out, and I'm left with 2 over 9. Here are 3 more examples. Pause the video and see if you can find the simplest form of these 3 fractions. Let's see what you got. A, 50 over 22. Well, I know 50 is 25 times 2, and 22 is 11 times 2. So the 2's can divide out, and I'm left with 25 over 11. For 9 over 90, I could use the 3's, but I know that 9 times 10 is 90, so I can leave the 9 up here and have those divide out. When there's nothing left in a numerator or denominator, there's an invisible 1. So this would be 1/10. 35 and 75 both end in a 5. So 5 times a 7 is 35. And 5 times 15 is a 75. And my 5's will divide out. And I have 7 over 15. If you can reduce 2 fractions to the same simplest form, then those 2 fractions are equivalent. So 3 over 9 can reduce to a 1/3. Well, so can 2 over 6, because here the 2's will divide out. When 2 fractions reduce to the same simplest form, then they're equivalent. But you can't always reduce them to the same simplest form. You may want to just compare to see which one is bigger than the other, or If you can't find any common pairs of factors, you may want to use something called a cross multiply. If I want to see if 6 over 24 is equal to 2 over 8, I can take the bottom of one fraction and multiply it by the top of the second fraction. So here I would say 8 times 6. 8 times 6 is 48. Take the bottom of the other fraction and bring it to the second fraction numerator to multiply, and 24 times 2 is 48. If you get the same product, if when you multiply them you get the same number, they're equal. Is 2/5 the equivalent of 4 over 11? Well, 11 times 2 is 22. 5 times 4 is 20. 22 is not the same as 20, and so these are not equivalent. Let's look at letter C. 2 times 15, is that the same as 7 times 8? Well, 2 times 15 is 30, and 7 times 8 is 56. They're not the same, so they are not equivalent. Pause the video and see if you can find the answers for A and B. Let's look at letter A. Letter A would be 5 times 22. Is that the same as 10 times 11? 22 times 5 is 110. Well, 10 times 11 is 110. So yes, these two are equivalent. 7 times 24, is that the same as 21 times 8? 7 times 24 is 168. Well, so is 21 times 8. So again, these are both equivalent. They're the same fraction. And that's how you can use prime factorization to reduce fractions. And if you aren't able to find any pairs that match, you can use cross multiplication.